Okay, good afternoon, everyone. My name is Michael Luke. I'm a particle physicist in the Department of Physics, and it is my pleasure to welcome all of you here today to the last of this year's Welsh lectures, which is the second lecture by Professor Cumran Vafa. As Professor Pete noted yesterday in their introduction, Professor Vafa's contributions to string theory and quantum gravity over the past few decades have been extensive and profound, making deep connections between geometry, topology, and physics. He's particularly known for his work on gauge gravity duality, black hole entropy and the counting of microstates, mirror symmetry, F-theory, the weak gravity conjecture, and what's known as the swampland program, which aims to delineate the boundary between consistent and inconsistent theories with quantum gravity. He's been the recipient of the Dirac Medal, as well as the Breakthrough Prize in Fundamental Physics, and has been elected to the National Academy of Sciences. Now, yesterday, he told us about fundamental lessons from string theory that string theory has given us into the nature of quantum gravity, in particularly the counterintuitive non-decoupling of long and short distance physics. And today, he will give a colloquium about string theory and predictions for our universe. So please join me in welcoming once again Professor Cumran Vafa.
Thank you. Thank you for the kind introduction. It's a pleasure to give the second lecture here. Basically, it is going to be related to the discussion we heard yesterday, the talk I gave, but more meat into it. So we kind of explain it a little more in more detail. So quantum field theories without gravity included are well understood. So we have these beautiful diagrams that, Feynman introduced, I don't know, close to 100 years now, near 80 years or so ago, where you kind of explain what happens in quantum electrodynamics by, considering all possible paths these particles take and summing over the past histories of all processes like these. Here, electrons going and going forward and backward. What happens here? I guess we went forward very fast. So you see these exchanges of photons between electrons, and this gives you all the kind of predictions that we have and experimentally check that this is a sound idea and it works beautifully. And more generally, this has been extended to other forces and it works beautifully. So we understand what quantum field theory is. As long as we don't include gravity. If you did the same thing with gravity, like one of these particles becomes graviton, and if you try to do similar diagrams and calculate them, then you would think there's not much of a deal. Namely, all you have to do is to remember that in addition to the action that we have involving gauge fields and matter fields and so forth, you also include the gravitational field, which is the metric, and then you also include the Einstein-Hilbert action, which is the curvature term. Couple them together, maybe add cosmological constant, whatever. Basically, the same story goes forward. You just have a fluctuating metric in addition to the fluctuations you had before. So you get fluctuating space-time, and also you can ask gravitons moving in it as representing of these fluctuations of the space-time ripples. Okay, so that's not a big deal. So what's the big deal? This approach does not work. The amplitudes defined this way, then the infinities that appear in Feynman diagrams are incurable. In fact, Feynman tried to do that and he failed himself. So he couldn't make it work. So his method did not work when it applied to quantum gravity. The most natural conclusion that one could draw from what Feynman's failure was that gravity cannot be coupled to quantum fields. You should never integrate or view metric as fluctuating. It should be fixed. Of course, that's not possible because in our universe, we know that the metric is not fixed. Otherwise, we would not have any gravitational force. Therefore, the idea that gravity should be mixed with the other forces seems to be a paradox because on the one hand, it says it doesn't work. On the other hand, we know it should be part of nature. Now, string theory offers a solution to this conundrum by replacing the point particle perspective of graviton with a looped version of it. That is, gravity is not mediated by particles, the gravitons, but actually by loop-like objects, loops of energy, which is, in this case, represented by the string. This turns out to lead to consistent quantum theories of gravity. Just this idea, the simple idea, solves the problem. Basically, what that means is that the Feynman diagrams that Feynman was studying should actually be viewed as replacing each point by a loop and doing everything else the way the diagram suggests we should be doing. So you get these surfaces instead of these diagrams representing the physical process. Of course, you notice that if the circle, the string, shrinks to a point, these diagrams look like this. So basically, these are just fattening up of the Feynman diagrams, just representing word lines by, word sheets. So basically, the idea is very similar. So of course, this can easily be mistaken. This can easily be mistaken with this if the radius of the string is small, and that's what's going to happen when the string is not stretched too much. In fact, the lowest excitation of a string is an unstretched string, which is like almost zero-size string. So naturally, this would be a typical diagram that would arise. So that's why we would have missed these diagrams, this way of thinking, because if we talk about low energy, we are talking about the lightest particles, and we would not be talking about these bigger ones, which could be excitations of these strings. Okay, sounds so good. So what's the big problem, or what are we going to say is the implications for our universe? The natural question is, can we get everything consistent looking in quantum field theory in 4 dimensions coupled to gravity from string theory? String theory comes with 6 extra dimensions for space-time, and these should be viewed as 6 extra space dimensions, and therefore should be somehow viewed as tiny. Otherwise, we would be contradicting the fact that we don't see them with our eyes, so to speak. It somehow would have impacted us way too much if it was really big. So they should be presumably very small. If it's possibly wants to be in our universe, that should be somehow hard to detect them. So then the question is, what are the extra dimensions? These 6 extra dimensions, they can have different shapes, sizes, and so on. Yes. Well, so this is a cartoon of how they would look like, for example. So imagine the extended 3-dimensional space represented by these Cartesian 2-dimensional grids of these golden grids, so to speak. And look at the space above. At each point, you can think about the space existing as some compact 6-dimensional space. Here I'm representing these curved kind of shape there. Now, here it's like moving around in time, but usually we think about them kind of like static or not moving too much. So it's kind of frozen. And moreover, we think usually they're the same everywhere on these points. So even though you can kind of vary what's going on in internal space at each point, for the ground state, for the lowest energy situation, you would think it's not moving much anywhere. So it's kind of extra piece attached to each point. That's how you should think about these extra dimensions. So what is going to happen is these extra dimensions will have some bearing on the physics. For example, if your extra dimension is a 2-dimensional torus, you can wrap a string around it one way, and you get 1 particle. So at each point, you can put a string, and you get a particle viewed from the perspective of 3-dimensional space-time. 3 plus 1 looks like a particle here. And depending on which one you have different spectrum of particles depending on what configurations you consider. So the geometry and the topology of this extra dimensional space will impact what we will see. So even though it's tiny, it will have some implications about the particle physics and observables in our universe. So depending on what you put here, you'll get totally different physics at long distances. So you choose something, you geometrically pick something, and then pops out the physics that we get in 3 plus 1 dimension. It's kind of like a dictionary where geometry, it's a cookbook. Geometry, you put this here, and then pops out physics. That's roughly the way it's happening. So one geometry might give you gauge forces related to SU4. with maybe 2 generations of particles and so on. And another one might give you a different gauge symmetry, gauge forces, and different representations for the matter with different charges. So you ask, okay, suppose I'm not interested about how the extra dimension looks like. Who cares? I'm only interested in what I'm going to see in our universe. Who cares about how you got it? That's a valid question. So if you're not interested in this, you could ask the following question. Can we get everything? And if we can get everything, then forget about how you got them. I just can use whatever I want. Okay? That's a valid question. It simplifies the task, right? You don't need to go through geometry. It seems that we cannot get arbitrary quantum field theories. And in fact, the set of theories that we get are finite. So it's far from being able to get everything. It seems actually almost you can get almost nothing. Well, finite out of an infinite set is measure 0. That's why I'm saying almost nothing. So it is quite surprising that you can get almost nothing out of this in this form. So for example, if you talk about maximally supersymmetric theory in 4 dimensions, what's called n equal to 4 supersymmetric gauge theories, coupled to gravity, the rank of the gauge group we get is always less than 23. That means you cannot get too big a group. For example, if you take SU24 and try to couple it to gravity with n equals to 4 supersymmetry, it just doesn't work. The theory does not exist. So out of all the SUNs you can put, SU1, SU2, SU3, all the way up to S trillion and up to infinity, only just the first 23 of them could be done, not the rest. That's remarkable reduction of possibilities. So you see, when we think about standard model, we say we have SU3 times SU2 times U1, and you may have wondered, wow, why is just such a simple structure of a group? Even though we know quantum field theory perfectly is fine with much bigger groups. SU 10 billion or SU trillion is perfectly fine. We don't have it in our universe. Why? See, here we are learning that if you have enough symmetries, it's not even consistent to consider too big a gauge group. That's quite remarkable. That means that potentially ignoring gravity, consistency of gravity, is leading us to a wrong prior that everything is possible, whereas actually it's not. And if somebody said I have a gauge group in that universe, which has n equals to 4 supersymmetry, which is only SU15, it's actually a typical number. SU trillion doesn't happen, SU 1000 doesn't happen. So that's a natural explanation of why it sounds fine-tuned. Why is the rank of the gauge group not big? So what we learned from this simple example is that not only you can actually see this from string theory perspective, you cannot get them, but actually you can argue that no theory of gravity would be able to describe this. It's not just that string theory is unable to give you this. You can explain what goes wrong with theories with more than this rank. So it's a problem beyond string theory, even though it was first discovered in the context of string theory. So what we learn is that the generally consistent quantum field theory cannot be consistently coupled to gravity. So in a sense, Feynman was right. Quantum gravities cannot be coupled to quantum field theory. Only very specially chosen quantum field theory by some magical things can couple to gravity. Otherwise, generically, it just doesn't work. Now, this raises 2 questions. Does the fact that most quantum field theories do not arise in string theory, deficiency of string theory, or general conclusion? Here, as I said in the context of this example, in that example, you can actually show it is not a deficiency of string theory. And in fact, more generally, evidence is emerging that the theories that we get from string theory and being finite is also explainable by basic principles of quantum gravity. So it's more general than just because we are using string theory. And the connections arise when you try to fold into the discussions aspects of black hole physics, unitarity, and quantum consistency of black holes. Black holes play a central role in a lot of parts of quantum gravity. It's not just they are cool objects, but they actually have very big implications for consistency of the theory. So then the question is, what criteria distinguish a good theory, good quantum field theory, which is what we call part of the string landscape, from bad ones, which we call part of the swampland, which do not arise in the consistent theory of gravity. So this delineation we call the swampland program. Now, you might ask why we call it the swampland program instead of the landscape program. Because after all, we are interested in what is the solution, not what's not the solution. The answer is simple. It's much easier to say what is ruled out, because that's basically all there is. Everything is ruled out almost. So it's much easier to say this is not good, that's not good, that's not good, because the set of possible good ones is measured zero. It's almost impossible that you can pinpoint exactly what is good. So it's much easier to actually put a condition like theories on the left side are bad. So all of them go out. And theories on the right side are bad, and so forth. So you can kind of put lines or surfaces of possible parameters which delineate good versus bad. But to pick a point that this is good is much harder. So that's why we have a swampland program, which tries to precisely say which theories are bad, what criteria are bad, and the good theories are on which side of it. It's, of course, not going to be easy to completely narrow down which one is a good theory, because they're much harder to say which point is actually good. So the way you think about it is that each example that we know in string theory can lead to a good one by definition, because we know string theory works. So therefore, we can produce some finite set of good ones just by studying the string landscape. So that's what we call the landscape, and we can relate this as a good one. So generally, we should think about the space of all quantum field theories as this green space here. And except for a few jewels, which are consistent points in the quantum gravity landscape, which one of it is presumably our universe where we live in, the standard model, the rest of them are bad. And so the task is to try to kind of, even if it's going to be hard to figure out exactly which one is ours, it might be easier to say, well, which side is not good, and so kind of narrow it down. This also gives you a prior of where the good theories are, which actually makes some fine-tuning looking things explainable just by the fact that they arise in a very, very specific corner of the allowed quantum field theories in general. Now, I will tell you now more detail about some of these criteria are. Some of them I touched upon yesterday, but now I'm going to try to explain how they arise. Where do we get these from? So the criteria I'm going to tell you are not the only criteria we have found, but these are some representative examples of what criteria the swampland program has come up to distinguish good versus bad theories. So in a good theory, we don't have a global symmetry. Theory of quantum gravity is unique. All the charges that appear, that can appear in a gauge theory, like electromagnetism, should appear. The range of fields in a quantum gravity theory is effectively finite. This case relates to the duality conjecture I described yesterday in detail, but now I will go over it. The theory must admit higher dimensional objects like in string theory. Gravity is always the weakest force, and there are restrictions on critical points of potentials which are positive, and it has some cosmological implications. So these are the list of things, some of which I have already touched upon yesterday, but now we'll go over it in more detail. Some very basic facts about black holes that we will use. Suppose you have a fixed electric charge Q and a mass m. Then as long as the mass in Planck units is bigger than the charge, there is a black hole. By that I mean you can solve Einstein's equations and you find a nice solution, black hole solution, short charge solution. The extreme case where mass is equal to charge, more precisely, you might think about it as m over m Planck, or equal to the charge, can also occur, and this is called the extremal black hole. Black holes have thermodynamical properties that Wittgenstein and Hawking discovered. In particular, they carry an entropy proportional to area, which is given by 1/4 of the area in Planck units, where area is the horizon area of the black hole. Okay, so let's go with the global symmetry. Suppose you have a charged object which doesn't emanate any electric fields. So it's charged only under symmetry. So you want to count the charge. I want to argue that the charge, so just imagine this would have been an electron, let's say, but without any electrical field emanating. So that's what I mean by global charge. Suppose there's no electrical field associated with the electron, and you would throw it into the black hole. In that case, I'm going to argue that the black hole gets rid of the charge conservation. How does it do it? We'll throw one in, and what happens is that Hawking taught us that the black holes evaporate to nothing. And you might say, wait a second, when it evaporates, how does it evaporate? It gives us particles out. So you say, okay, if it gives out particles out, then it will create, maybe it gives back the same charge back. The problem is the Hawking also told us how does it evaporate. And you can see that there's a symmetry between the charge and the minus charge. So it gives equal amount of charge and minus charge. And therefore it evaporates them equally. And therefore you start with something which you threw in a charge, but now you have no charge left out. Therefore you have violated charge conservation of that charge you put in. That's simple. Now you might say, how did it happen? Well, the simplest way to say what happened was that from the black hole perspective, the evaporation happens at the horizon, and at the horizon right outside the black hole, you cannot even measure the charge, because how do you measure a charge? Well, if there was an electrical field associated with the charge, you use Gauss's law. You take this electrical field emanating, and then you would do Gauss's law. But a global symmetry has no electrical field associated with it. There is no way to measure it. And that's why the evaporation of the black hole is equal for charge and minus charge states. If it did have electrical field associated out, then the evaporation will not be symmetric between charged and minus charged one. It will try to get rid of the electrical field, and therefore it will evaporate more of the charge that you put in. And that's how the charge conservation would work if they were associated with some electrical field, which is gauge field. So there's no problem with having a gauge charge like in our universe. But if there was no electrical field associated with it, then that symmetry cannot be conserved. So these kind of ideas come, as we can see, it's not a very complicated idea, but black hole plays a central role. These ideas were discussed before string theory even were studied. So this is not a string theory statement, but just it's valid also in string theory. So it's the kind of thing that we learn to check with string theory, general ideas which doesn't need any string theory reasoning. We checked in string theory, that's indeed correct. That every time we actually have a symmetry, it's always associated with a gauge symmetry. You don't get a global symmetry in string theory. So the next one is that the quantum theory of gravity is unique. If somebody said, I have a quantum gravity, and somebody said, I have a quantum gravity, then there must be a way to get from one to the other. So for example, suppose on this side of the room, we have some quantum gravitational theory, and somehow on the other side, which may not be part of our universe, maybe a disconnected universe, you get a totally different gravity theory. The statement here is there must be a process where it interpolates from one to the other with a finite action process. In other words, physically allowed possibility. It cannot be totally disconnected universes. Now, how does that work? Why is it? Well, the idea is actually quite simple. In the context of string theory, for example, to get a universe, you choose an internal manifold. So suppose you do one of these curly kind of spaces I drew for you, a 6-dimensional one, which is complicated, and somebody else does a different one. So somebody chooses M, and somebody else chooses N, and then you get totally different physics down here. And it might be that M and N have different topologies, for example, and therefore you might think that you cannot deform one to the other. So mathematicians study the spaces of how you deform from one to another. This is what's called the cobordism class. And they sometimes get, depending on what conditions you put on your manifold, you sometimes get different inequivalent classes. They find some M's cannot go to some N's. They, in fact, get a group law. You can associate a group symmetry, which distinguishes which ones can go to which ones and which ones cannot. So mathematicians are perfectly fine with having not all of them be possible. But if that's the case, that group law that they get, which is basically adding which manifolds can go together and which ones cannot go, gives you a global symmetry. But I just argued for you global symmetry is not allowed. So global symmetry is not being allowed actually rules out the impossibility of going from one to the other. So everyone should be possible to connect it to everybody else. So quantum gravity is unique. So just that simple idea of symmetry conservation tells you that. Think about it this way. You can think about this manifold as a choice, and the corresponding symmetry associated with it should not be protected. Namely, if you have somebody says, I have an M and I have another N that they cannot go from one to the other, then you can throw that M into a black hole. You can create a little local excitations of the space involving that manifold, throw it into the black hole, and then you can also get out, throw in an N, and so you cannot distinguish M versus N. There's no way you could have said which one is which. Therefore, that means the process should be possible to move from one to the other. So lack of global symmetries implies that there's no two different quantum gravity, it's just one. This is the example I was just telling you. You can think about this, a bubble of this manifold, throwing in to this black hole, and from the outside, you don't see the manifold. So there's as if there was no manifold. Oops, what's going on here? This is very fast forwarding, much faster than I was planning. I'm going fast already, but I don't want to go this fast. Somehow this is not, control of this is very tricky. Okay, very good. It's not going forward. Okay, this is the next one. Suppose you have a gauge theory like electromagnetism, what we call the U1 gauge theory. I want to argue that all electrical charges must be in the spectrum. So in our universe, we have, for example, quarks, 1/3 and 2/3 charges, and electron charge 1, and so forth. So the basic units for the U1 charge is 1/3, let's say. So all the charges appear. It could have been that you only get even charges, for example, or some other multiple of the basic one doesn't exist. Or it could have been that you have electric field and magnetic field, but no charge at all. You know, you can write the Maxwell's equations, and suppose there's no current or charges. What's the problem? The equations make sense. You can couple that to gravity, so there's no electrical charged object. What's the problem with that? The claim is that that can never be the case. You cannot have just electric and magnetic field with no electrical charged objects. In fact, you must also have magnetically charged objects. So for example, in our universe, we must have monopoles, magnetic monopoles. So what's the argument for that? Well, I was explaining that if you take a sufficiently big mass and big charge, as long as the mass is bigger than the charge, there is a solution to Einstein's equation. This itself is like a particle. A fat, big black hole is like a particle. In fact, more than that, there are many particles which have the same mass and charge according to Bekenstein and Hawking entropy. There are exponential of area over 4 such particles, roughly. Yeah, so therefore, there's a huge number of particles with that mass and that charge. And in fact, you can take another one which has the same mass. You can take one which has the minus that charge and something which has charge plus 1 of that and put them together, and you get that basic unit of charge you want just by colliding these two black holes. So you get whatever charge you want in your theory. So black holes also imply all the charges are there, including magnetic monopoles. Because I could have thought instead of electric charge black holes, there are solutions with magnetic charge. So that's a prediction. We are saying our universe must have a magnetic monopole. So if people say string theory does not have predictions, this is a very concrete prediction. It has not been observed yet. It's not a post-prediction, it's a prediction. There is a magnetic monopole in our universe. There should exist. Now you say, okay, can I say anything about else just like this? I would say a few more things about it, at least one more thing about it. The next criteria is that the range of field is finite. So suppose you have a scalar field phi, and without gravity, we usually have no restriction on its range. We say, well, phi is a scalar field, a real field. Its values from all the way from minus infinity to plus infinity. So what? It's not a big deal. That's what we always kind of have no problem with it in field theory, and we just talk about phi as if it belongs to real numbers. However, with gravity, it seems the range of this field for a given effective theory is finite. In other words, if you start with a given theory, with a given cutoff in your theory, there's only a finite range that this theory is good. And after that, it breaks down. So effective field theories give you only a finite range, and that range for the field space is order 1 in the fundamental units, the Planck scale. Now, to try to explain this using black holes is not easy. It's not easy. We don't have a clear explanation of it using black holes. There are some ideas to try to explain why this happens, but this is one of the hard things to explain from bottom up. But this thing is one of the most important discoveries that we have made in string theory. And this is because it relates to a feature or symmetry discovered in string theory called dualities, which I was explaining to you yesterday. The fact that things morph from one to the other is exactly the point that things break down. In other words, the description only is good for some region. If you go to one extreme, you get a totally different description when you go to the other extreme. And the way that happens is that you get some very light particles that change your description. So therefore, that finite range validity is also in line with expecting dualities on the both sides of the theory as you move around in field space. So in the field space, if I draw, for example, here, you can have one real number, but you can have multitude of fields, many dimensional field. In the field space, you can, if you're a given point in your parameters, you can kind of be like here. But if you go to the extreme parameters, you can get dual descriptions like I was drawing for you yesterday on the plot if you were there. But also you should think about these parameters as corresponding to the sizes or the geometry of these extra dimensions. So as you change the radii or the shapes and all that, corresponds to moving in this space. So these directions might be opening up some extra dimensions or some space shrinking to nothing. And these kind of parameters are these limits. And so what happens as you go in these directions is that as you go to the extreme values, you get exponentially light states. The mass of towers of state that you get this way goes exponentially with the distance in the field space phi. So you get an infinite tower of particles whose mass separation scale goes exponentially down. And that's why your effective field theory is valid only before you get there. So here I want to make a comment, which is an application of this simple idea. So before I go there, I want to say one fact here. So here, we get a tower of light states. We expect a tower of light state by the duality conjecture, which is valid in every example that we know in string theory, but actually more is true. The tower is weakly interacting. The tower includes particles which are not interacting much with anything. They're more like gravitational interactions. So they're very weak. So the tower is there, but more than that, there's a weakly interacting tower. So one application of this is the following. The cosmological constant itself can be viewed as a parameter. And you can view it as a distance in the field space. And it turns out naturally parameterized by exponential of that field. And so the tower of particles being exponential in field space implies that the mass should be a power of the cosmological constant. Cosmological constant in our universe is like e to the minus 300. So it's much more than order 1 number. It's 100, 300. And so this is a very small parameter, 10 to the minus 120. And so therefore, we expect to have a tower in our universe. A tower of light particles in our universe. Where is that tower? I didn't hear about tower. Did you hear about the tower? It must be wrong, because otherwise you would have heard about the tower of weakly interacting particles. Weakly interacting with everybody. That's hard to see them, like dark matter. Oops, could it be dark matter? So we may have heard about this already without knowing. So the tower of light particles naturally sounds connected to potentially dark matter itself. We are expecting the smallness of the dark energy to expect with the dark energy a matter with a mass very much linked to the value of the dark energy. And in fact, if you look at the constraint, what this parameter of order 1 is, you can use the combination of theoretical arguments and observational constraint to find the only option is A is 1/4. And what this would correspond to is the fifth dimension, one extra dimension among these 6 extra dimensions. One of them should be bigger than the rest, of the order of a micron. And that's what we call the dark dimension. Dark because it's related to dark energy, but also because the dark matter turns out to be the gravity waves in this extra dimension. This is what I was describing, showing to you yesterday. So we would expect naturally a picture where the dark energy be connected to the dark matter. Of course, the Newton's gravitational attraction changes nature when you go in higher dimensions. The force law goes from 1/r² to 1/r³ when the distance between the points is smaller than a micron. So we think about our universe as a sheet or a 3+1 dimensional sheet inside this one higher dimensional space. And the gravity, these wavy things I'm drawing here is the dark matter representing basically these gravitons, which goes outside our world, and they're weakly interacting with each other and with us. So it's very hard to detect them. Only effect of them is through their gravitational effects, and that's what has been observed so far. So this model is another prediction. Gravity, this model predicts dark matter is not directly detectable other than its gravitational effects. Now, people have been searching for direct detection of dark matter, and so far nothing has shown up. This predicts that that's going to continue to not show up, except for its gravity imprint. That's another prediction. In fact, the other prediction here that I was mentioning is to say that there is a force law which goes like 1/r², and people actually are doing experiments now in Vienna to try to check whether that's the case. And the experimental setup is something like this. So you have a rotating disk and a pendulum, which is kind of getting resonating based on the resonance frequency of it, attracted or repelled from it, depends on which region you're in. And you get a potential signal once you put these close together in the distance scale of about micron. Now, you might say, when is this going to be done? Well, it's actually not, the experiment is not that simple because of various noise issues that you might expect, but they are trying to push it down to 10 micron now. And they think within a couple of years, they will have at least gotten to 10 micron. We'll see if that's the case, but that will begin to potentially get to the regions that we hope that they will see some new signal of deviation from 1/r² force law. Why is it going so fast suddenly? I'm not pushing it that much. Okay. Okay. The next criteria is the existence of extended objects. Well, string theory is a theory of not point, but extended object, which is one-dimensional string. Why should it be like this? This actually gets related to the same thing we said about the statement that the field space is finite range. So let me explain how that comes about. Why should we have extended objects? Consider the theory you're in, and consider compactifying the theory. What does it mean to be compactifying the theory? It means take one of your spatial dimensions and just declare them to be periodic of a given radius r. That's what we mean by compactifying. So take, for example, this room, and just imagine that side of the wall and this side are glued together to become a circle. That circle of radius r can be described. This clicker is not very effective. Let me just go over this side. Maybe that helps. So, so the radius of this universe will be given by e to the phi, which is the scalar field I was telling you about, with the Lagrangian, which is like 1/1/2 grad phi squared. So If we take a case where the radius is much, much bigger than 1, then the phi is much, much bigger than 1, bigger than 0. And as I told you, when you go to the large distance in field space, you should expect a tower which goes exponentially in phi. In this case, it's obvious what that tower is, because 1 over r, which is e to the minus phi, is the energy scale of the graviton waves on this extra circle, like n over r that we are familiar in quantum mechanics. Indeed, you get a tower of these light excitations of these waves, which go like n over r, and that's the tower. So the tower is just a tower of the kk modes, or just these long wavelengths, various harmonics of it. That's that tower. However, we can also go the other way. We can go to phi minus infinity. And that corresponds to shrinking the radius to 0 side because of the relation between radius and phi. But I just told you that in each direction, we should get light tower. So suppose we take this universe, the one we are in, and identify these walls and bring them together. And the statement is that there's something light has to appear. A tower of light stuff. How does that happen? In fact, if you take any quantum field theory, and if you did this, what you get in this limit is that you just freeze some particles that you had before. Basically, you just get no tower. You just get rid of some degrees of freedom you have, because the harmonics that you put in is not allowed anymore. The waves they're coming very heavy. And basically, you just say that all the fields that you started with will not be able to depend on this extra dimension. This is what we call the dimensional reduction of the field theory. You don't get any light particles. So any field theory, any particle theory will not give you a tower of states. If you're expecting a tower of states, something else should happen. How can you get a tower which depends on the identification of these two walls? The only way this could happen is that there's some state, some kind of entity that knows about the global topology of the space. That cannot be the case unless the object you're talking about is extended, that can be connecting the two sides. So the only way you can get a light tower is that you must have extended objects, like strings or membranes that can have to wrap around this extra direction to see that's getting small or large. If it was local, it will miss this fact. So point particle will not have this feature. Extended objects will have this feature. So dualities and this feature that the effective range is bounded necessitates existence of extended objects like strings or membrane. So that's what I just explained, that we needed these objects to get the finiteness of the field range working. The next criteria is that the gravity is the weakest force. In our universe, as I explained yesterday, as I mentioned yesterday, the gravity is the weakest force. Like electric repulsion between electrons is much stronger than the gravitational attraction between them, because the mass of the electron is much smaller than its charge in Planck units. In fact, since the electron is 10 to the minus 23 compared to 10 to the minus 1 for E, indeed, that's correct. So this is a very weak force. In fact, you will not get, it's basically incomparable as far as the ratio goes. It's almost 0. So this is true, but this is also, we claim, true in any universe, not just in our universe. In any universe, you should get, first of all, you should have charged objects, because I explained that every universe, every quantum theory of gravity must have charged objects. It cannot not have it. And secondly, I'm saying that their mass here has to be less than the corresponding charge if you measure the mass in Planck units. Why is that? Again, black hole explains it. How does black hole come to explain that? Well, consider the extreme case of a black hole where the charge is equal to mass. And let's do the following. Suppose, remember that this has to evaporate according to Bekenstein and Hawking by emitting charged objects. Suppose it emits a charged object of a little charge Q and little mass M. Then the charge and the mass of the black hole change by the mass going to mass M minus small m and the charge going to Q minus small q. But for the black hole to exist, the mass of the black hole should be bigger than or equal to its charge, which means m minus small m should be bigger than q minus small q. But we started with q equals to m. That means that the mass that it emitted must be less than or equal to its charge. So there must be mass states which have this property less than or equal to the corresponding charge. The equality can only occur for the supersymmetric case, what we call the BPS states. In those cases, the decay of the black hole can be prevented, in fact. Only in the supersymmetric cases. Otherwise, it will always emit. So this is kind of a linking between the black hole ideas and the statement that the gravity is the weakest force. Now, there's further evidence for weak gravity conjecture. You can take pure Maxwell theory, electromagnetic field, and couple it to Einstein theory. This leads to naked singularities, that these are singularities that are not hidden behind the horizon. And you have regions with strong electrical field, which leads to these naked singularities. So you can find solutions to Einstein's equations. Originally, you start with a background which has no singularities. You crank up the electrical field, and you find that the gravity creates a singularity, and the singularity is not cloaked by horizon, so you can actually see it from far from the singularity region, unlike the black hole and other singularities of C that are supposed to be good in the GR. These are naked singularities. Penrose, for example, has conjectured these cannot happen in any context, but now they seem to happen. What do we do with this? Well, actually, the claim is that in this situation, a pure Maxwell theory, which is electric and magnetic field only, is not allowed. First of all, you must have charged objects. As I explained, completeness of gauge theory spectrum. There must be charged states. Secondly, the weak gravity state, not only there are charged states Q, but their mass cannot be too high. Their mass is less than charge. So when you try to increase the electrical field, if you put these in the theory, as soon as you increase the electrical field, since their mass is small, you pair create these charged particles from the vacuum. And they screen the electrical field because they're light. They can be created, and they screen it, and they avoid the naked singularity. And you can see, actually, you need exactly m is less than or equal to q for this to be avoided. So that's precisely the bound you need for it to avoid naked singularity. So this is a completely independent idea, and it again gives you this statement. So these statements are actually consistent with what we have seen again in string theory, even though the argument has nothing to do with string theory. I didn't mention the word string theory in this part, but it's true and it's consistent. So there are these bottom-up arguments which have nothing to do with string theory, but actually are confirmed by the examples that we know in string theory and our universe. So a prediction of our universe is that the electron's mass is less than its charge. More precisely, that's a postdiction, because we already knew it. But we actually can make another postdiction, which is the following. There is another application of the weak gravity conjecture in our universe, which is like De Sitter almost, which has positive cosmological constant. Not only m should be less than q, you can actually study evaporation of black holes, large black holes in our universe, a black hole which is as large as our whole universe. If you study that, you find that m should also have a lower bound, which is given by the cosmological constant to the 1/4 times q to the 1/2. This basically, if you put it in numbers, you find that the mass of the electron should be bounded by these two numbers in Planck units. This lower mass scale turns out to be close to the neutrino mass scale. So this predicts that the mass of the neutrino should be below the mass of the electron. So now we are beginning to get closer to a non-trivial statement, which is again a postdiction, because yes, we know it's true, but this actually said it had to be the case. And now it's relating the dark energy to the relation between the electron and the mass scale of something which is close to the neutrino mass scale. Quite remarkable. So these are connections between cosmology kind of data with particle physics data coming from consistency of quantum gravity. There is another prediction, which I forgot to put on this side. Monopole is another example. Monopole is a charged object, magnetic charge, and we argue this should exist. But the weak gravity tells you that this mass, where was it? Here, the mass should be less than or equal to its charge. What is the magnetic monopole charge? In the fundamental units, it's if you work it out, it's the inverse of the electric charge, so it's 10, around 10 or so. And that means that the mass of the monopole should be less than or equal to 10 in Planck units. In other words, we are making the prediction that the mass of monopole better be less than 10 to the 19 or 20 GeV. Again, another prediction. So, and not only monopole should exist, its mass cannot be too much higher than 10 to the 19 or 20 GeV. Very specific prediction. Okay. Where do we go? Okay. Restrictions on critical points of potentials for positive potential. An important question for early cosmology, and in fact, late cosmology. In the early cosmology, because it might relate to inflation, and late cosmology, because it might be related to dark energy, is what is the shape of allowed potentials in the quantum theory of gravity? So typically in inflation models, people consider flat regions of potential where you have some range of field space where V is constant for a while. And this allows the conditions to be suitable for what's called the slow roll inflation. So you can have a field kind of moving gradually and to causing the universe to exponentially inflate at the early epoch of the universe, and then maybe settle down to some lower value of energy, which presumably is related to what the dark energy values measure today. This is one picture of how you could get both inflation, early cosmology, and late description of dark energy in one picture. Are there any restrictions on this potential from fundamental quantum gravity reasoning? This turns out to be a difficult problem for us to make predictions. Why is that? It turns out that any situation for which the potential is positive must break supersymmetry. And it turns out that once you break supersymmetry, all the analytic controls we have, explicit calculations, become difficult in string theory. That's one problem we have. Nevertheless, it turns out we can make some statements, which is what I want to explain now. Even though supersymmetry must be broken, you can study the theory in the far corners of this field space when you go to asymptotic values. As I mentioned, these are regimes where your theory becomes weakly coupled and you have a dual description, so you can calculate the potential by just perturbation theory. And you find always when you compute the potential in these perturbative limits, the potential invariably goes down to zero exponentially fast. So the potentials always die off in these limits. It's a feature of string theory. More than that, we learned that, for example, the slope of that, namely if you look at exponentials, at the asymptotic infinity, if you go far away into infinity, the slope is bigger than square root of 2 in fundamental units. So it is far from a flat situation. It's exponentially going down. That's quite a concrete statement. And in fact, you can show that with this value, you cannot have an inflating universe asymptotically. You know, inflation cannot happen here because it is too steep. It turns out that square root of 2 is precisely the boundary between inflating and not inflating. So this is not possible to inflate the field here. So this is only in the asymptotic regime of field space. What about inside here? What can we say about regions in the middle? Could we have, for example, a situation like this? Maybe. You can have perhaps a minimum here and something else. But notice that even if you have a situation like this, the fact that the potential goes to 0 at infinity implies that's not stable, or more precisely, it's at best metastable. So you can at best have a metastable situation, not a fully stable one. You know, the potential cannot come up and stay up. It has to go down to 0 somewhere. And therefore, we can always tunnel out of this positive one. So the fact that we have measured positive energy in our universe suggests has the following prediction that we make is that our universe must decay or is rolling away to decaying process. Now, this is not a prediction I wish to prove because it's a kind of a disappointing prediction, but that's a prediction, unfortunately. Our universe is not here to stay. But here I was just talking about the boundary behavior, but I want to say something about here inside. What do we know about inside? Because that certainly is interesting and we want to access somehow. This is difficult, unfortunately. So what is going on inside is precisely hard because the theory is not weakly coupled. There's no perturbative expressions that we can trust. The perturbative methods break down because you're far from the easy regions, these asymptotic regions where you have a simple description. So what do we do? Well, there could be a bunch of options. For example, there could be no restrictions. Well, by now we have learned that's not the right answer because there's so many restrictions in the theory. The theory is finite number of sets, so cannot have no restrictions. Question is, what is the restriction? Whatever the restriction is, must be that at infinite distance gives you these exponential bounds I was telling you about. So what reasoning, what kind of a physical principle could be that gives you not only these exponential decays of the type we have, but also says something from in the inside? So one idea, and this is an idea that has not been proven but has been proposed, is what's called the Transplanckian censorship conjecture. This idea says that if you have an expanding universe, you cannot have a situation that a region of space which is smaller than the fundamental length scale in physics, the Planck scale, can grow by a factor of growing factor of the radius of the final universe to the initial. It cannot grow to be bigger than the whole size of the full universe, which is 1 over the Hubble parameter. So this is basically a conjecture that it can never happen, that this can never happen, it should always be below it. Why is that conjecture even reasonable? The reason it might be reasonable is that regions smaller than the Planck scale should not be physical because we don't think any length smaller than the Planck length is physical. So if a fluctuation happens in smaller scale than Planck, and it expands out to be bigger than the universe, it cannot grow anymore, it freezes out. And if that region, for example, comes back to our universe, you're basically viewing a perturbation of a sub-Planckian thing which cannot be physical. So how could that happen? That should not be possible. So this is motivated from that principle. It turns out that if you put that principle, you get that all the potential should go asymptotically down exponentially fast with at least square root of 2. So you can actually use this to actually derive that square root of 2 I was telling you about, which is observed in the string theory example. But it also gives more prediction. It tells you that this kind of situation that you have a hilltop maximum can happen, but the instability should be sufficiently large. Namely, the V double prime over V should be order -1 in Planck units. But it could also allow metastable dissipation as long as the lifetime is not too long. It could be Hubble state, Hubble time up to log corrections. It turns out that these predictions of order 1 are consistent with the recent results of Desi and Des and so forth if you combine them. And so it's quite exciting that this may actually be the case, predicting that these numbers are order 1. You see, this is very non-trivial statement because if you look at the potential, you just say potential could have any slope a priori. Without, if you have no specific prior, you would have said V prime can be anything. Now, if V prime can be anything in fundamental units, you wouldn't choose 10 to the minus 120 as its value. If somebody said it's smaller than 10 to the minus 100, you say, come on, it better be 0. But here we say, no. Remember, V itself is small. So the slope could also be very, very small if the order parameter in front is order 1. So this says that don't think just because the slope is of smaller than 10 to the minus 120, it has to be 0. Because we are expecting it to be of that order anyhow. So these are kind of the priors that string theory brings. And this is what prediction we already made like 7 years ago. And this is actually, I would call it a prediction that if you observe that V is changing, the natural slope should be order 1. And this is consistent with Desi. So this is, I would say, not only a prediction, potentially going in the direction of confirmation of a prediction of string theory. So it's very exciting. So there are some aspects of the Swampland program that makes predictions about inflation. In particular, it tells you some restrictions on large field inflation. And also the Transplanckian censorship conjecture implies that if there is an inflation, the scale of it is much smaller, which is smaller than 10 to the 9 GeV, with the parameters of inflation, which is extremely small and fine-tuned. So this basically means TCC tells you inflation didn't happen if you believe it in TCC is the true principle. And you might ask, oh, inflation didn't happen, then what happened? If it's not inflation, how are you going to solve the problem of homogeneity or horizon problem and flatness, and what is the explanation of all that? Well, there are other explanations. You see, in the context of string theory, the early universe is very naturally described by a dual theory. It should not be described by our field theory. As I told you, the field range is always finite. When you move too much in parameter space, you will have to go to a different description. The description you have is breaking down, should break down. It is not a bug, it's a feature. It is not a good thing for the theory to say, no, I'm good for all ranges. That is actually a no. It should not be possible. In the context of inflation, the idea is that if you push back, if you go backwards in time in our universe, you find the universe going down and down and down, temperature going up, and somehow inflaton comes and saves the day, so to speak. Whereas this says, no, it doesn't have to be. What's going to go down, temperature goes up, and your description breaks down. You should have a dual description. And the dual description, in that description, the universe that we are made of, the particles that we are made of will be dinosaurs, will be very massive degrees of freedom. And instead, there are another description which involves light degrees of freedom, which we are not made of, which is the ingredient there. So what must have happened therefore in the early universe in this picture is that you have a dual description, which when you grow the universe, it gets converted to us, which is the analog of what in inflation people would call reheating. Reheating will be conversion from degrees of freedom from a dual theory to our theory, and it populates us. Now, why is it non-local? It's precisely because dual descriptions are non-local relative to each other. So the fact that there's a horizon problem in the cosmology gets naturally explained by existence of duality, which is a non-local phenomenon. So that's perfectly reasonable as a potential solution to the kind of problems that inflation point. Homogeneity would also be easy because there's no degree of freedom left in our universe. Our universe is empty before it got populated, so the population gets filled equally in all directions same time because of the conversion from a dual description. So therefore, this lack of locality and homogeneity is kind of built in. So I would say that these are quite interesting suggestions that the theory comes up with. And I already told you that TCC predicts that there's an upper bound to the age of the universe. Even if it's metastable, it cannot be more than 2 trillion years. This is from the Transplanckian censorship conjecture. So either of the conjectures, the de Sitter TCC, explain the why now problem. The question is that why the timescale associated to the measured value of the dark energy, which is of order of 1 over the square root of the dark energy, is close to the current age of the universe. The answer is that the lifetime of the current universe, the maximum age of the universe cannot be much more than that anyhow. It's at most higher than this by a factor of a log of that. Therefore, in a typical, if you measure a time scale in a universe whose scale is 1 over root lambda times log 1 over root lambda, a typical age is of order of 1 over root lambda, which is the age we are living in. And that's the time we are observing the dark energy. So in other words, the statement is that whenever you have a universe for which the dark energy is the bulk of the energy in the universe, you are not too far from the end of that universe. That's what that roughly means. So therefore, the very observation of dark energy is the announcement to us, guys, you're not too far away from the demise. It's not just the political situation that is strange, but even the cosmology might be strange. Sorry to say, this is a gloomy thing. I don't want to end my talk like this, but okay, where am I? Okay. So I have also argued here that the distance or duality conjecture unifies the dark sector because the smallness of the dark energy is giving you this light tower, which is weakly interacting, and the light tower is dark matter. So there are all these unifying ideas are coming from fundamental physics in context of quantum gravity to make specific predictions for our universe. So let me just then tell you that in the dark dimension scenario, that this extra dimension, it turns out the fundamental scales that we see in the universe are somehow related by a simple power law or a fractional power law related to the dark energy. So you see, in the differences of 1/12 roughly, so if you work in the Planck units, so think about lambda as 10 to the minus 120. In the Planck scale is 1 by definition in Planck unit. Lambda to the 1/12 is 10 to the minus 10, which is the 5-dimensional Planck scale. So it's about 10 to the 9, 10 to the 10 GeV. So that's the new Planck scale, which is the fundamental Planck scale in 5D. QCD scale, weak scale, etc., come to be 2/12, and there's an argument why it should be 2/12. So this is not just an observation. You can actually explain why it could be 2/12. The neutrino scale gets related to the size of the extra dimension, which is 3/12, which is again the right tower for the mass of the dark tower, as well as the neutrino scale, which is the milli-electron volt to electron volt region, and the same as the mass of the axion and all that. The Hubble parameter is lambda to 612, which is related to the current age of the universe, and finally the lambda. So these are in line with the potential answer to what Dirac raised. Why are the ratio of parameters appearing in our universe so large? And why they seem to be related by certain power of each other rather than some numerical factors in front. This actually is exactly along those lines, because there is a small parameter on universe, which is this lambda, and things are related by powers. If this lambda was order 1, these will be all order 1. But if lambda is small, everything else will be scaled with respect to this. So only one thing is unnaturally small, lambda, which we don't have any explanation. I'm not explaining why lambda should be small. But if you take lambda being small, then at least it will tell you there's a multitude of scales related to that power of lambda. So it connects all the hierarchy to just one parameter, the dark energy. So it's a fundamental reduction of the parameter space to one thing. So let me conclude. So swampland conditions can lead to potentially observable consequences for particle physics and cosmology. Almost all quantum field theories are in the swampland because they are the good ones are measure 0 in the allowed space. Therefore, fine-tuning, such as hierarchy problem, may end up having a totally different solution by taking into account the prior of these finite set of allowed solutions. There are severe restrictions on consistent quantum gravity theories, and they put severe restrictions on the light matter, predict the 5th dimension, and the new ideas, including duality, should play a key role in the early universe. Thank you.
Thank you for a very nice talk. We have time for some questions. One question over there.
Hi. So you talked about predictions of the magnetic monopole using the argument of the black hole. I'm just curious. I don't fully understand this talk, obviously, but is it then observable outside of the black hole argument, or is it?
Is it observable outside the black hole?
Yeah, the magnetic monopole.
The idea is that if you consider a black hole, which has a magnetic charge, it should be able to, if you have an extreme situation, like imagine a huge black hole with a huge magnetic charge, for which the mass of the black hole equals the magnetic charge. This should be able to decay. And the decaying of that predicts that the mass of what emits, the unit of magnetic monopole that emits, should be less than its charge. So that's the idea that I was explaining for the weakness of gravity, and that we can apply to magnetically charged black hole.
Thank you for the very interesting talk. So you just told us our universe is ending soon, and now I have to figure out how to break that.
Not soon.
It's ending.
Ending.
I have to figure out how to break that to my friends and family. So thank you for that. But I'm curious, from the perspective of string theory, is there anything you can say about what happens when we reach this time scale? What happens after?
So this is, in other words, we are moving towards the dual description. The dual description, I don't know. In other words, it's going to be not made of us. Or by us, I mean not even necessarily 3 + 1 dimensional space-time. A dual description. it's hard to predict what it is, unfortunately. It's going to be very non-local relative to what we are right now. It's going in some other direction. Could be just the fifth dimension is opening up, which is very possible. And in fact, that's one of the models that we are pursuing.
I'll wait for the microphone.
Thank you for a very interesting talk. So I would like to follow up on the previous question. So would this change be continuous, meaning that like, suppose there's like a fifth dimension opening up, it's like a smoothly opening
Yes.
up?
Yes, gradual. It's very like rolling on a potential. But at some point we gradually decay away, and the light degrees of freedom will become very massive in that situation. So
All right, thank you.
Nice talk. So X, Y, Z can be thought of as fundamental fields. And my understanding is that that has to curl up according to this large excursion conjecture. You have to have a dual element to make X correspond to phi, you know, but that's within the context of theory. So the question is there any manifestation of this to that there is a finite size to how big the universe can get, which I guess is probably H vacuum, that is to say.
the universe can get, but the universe is decaying away. So therefore, the energy that's going to decay is going to continue to decay. So the geometry of space, one direction gradually opens up. So the fifth dimension is opening up. So you have a totally different, you know, R4 becomes R5.
But there's no action if you go to extremely large excursions in X, Y, Z, which is what the universe does. That doesn't cause an effective potential that has a some kind of a special curvature associated with it?
Not necessarily. If you're asking what's the spatial, what do we know about the spatial slice of our universe? We don't, this does not tell you about that. I don't know a priori what to say about once you pass the Hubble horizon. What is the meaning of it in terms of the physics? I do not know. This idea doesn't tell you that. All it's telling you is that the part that we do see within the Hubble horizon is going to have an extra dimension opening up in that direction. Now, what happens beyond that, I cannot say.
But within the generality of string theory, aren't all of the dimensions a priori treated the same way? That is
Yes.
to say X, Y, Z, and phi.
Yes.
And so one should be able to map the swampland issues into standard three-dimensional space, or maybe not, but that's.
Well,
the question.
the dimensions are, as you say, you know, they're all on the same footing. There's not difference between X, Y, Z, and phi, except phi is periodic or close to being small
Well,
range.
that's the interesting question. It seems like there is a role for periodicity in the phis that you're talking about.
Yes, periodicity, or more precisely, the boundedness.
Yeah,
Yes.
exactly.
Yeah, so that's phi, but that phi is the fifth coordinate is not the phi I was talking about. The phi that I was talking about in this talk would be the radius of this fifth dimension.
Yeah.
Related. So there'll be a coordinate, let me call it, I don't know, Z prime or whatever, which would be playing the role of a point on this extra dimension whose size is that field, controlled by that field that can roll off. So phi is not on the same footing as X, Y, and Z. That phi that I was drawing here is just the radius of this extra dimension as a function of X, Y, Z.
Well, to a certain extent, X, Y, Z is the radius of the universe, so.
Well, X, Y, Z is a position,
Well, I'm
labels a
talking
position.
about, okay, the excursion X.
You can move in X, Y, Z, and then you can go to any distance you want, but the phi here represents only the radius of the fifth dimension.
Questions at the back? In the green first and then.
So thank you for the talk, Professor. I wanted to ask you about the swampland condition specifically. If there's any swampland condition that might explain the asymmetry of particles and antiparticles in the early universe, is there any kind of constraint on this that would lead to the kind of explanation of particles dominating?
Well, there is you need a CP violation, and out of equilibrium early physics, that's been proven by general reasoning for quantum field theory, which is also true in the context of quantum gravity. So swampland does not add a new perspective to that. That could happen. It doesn't have to happen, but that could happen the same way in particle physics we think it could happen. So it doesn't bring a new perspective, at least not so far as not yet at least.
Can you hear me?
Yes.
Thanks for your talk. I wanted to ask a bit more about clarification. You mentioned that you actually believe that inflation did not happen, but rather a dual description of the processes that happened at the early stages of the universe. Can you provide a bit more details about how you would describe and what description would model the dual model of early development of the universe?
So good question. I do not know, but I can give you a toy model. That doesn't mean that's our universe. So I would just give you what could be similar to what might be happening. So there's a symmetry in string theory called T-duality. T-duality tells you that if you take the universe and shrink it to a size smaller than Planck, let's say, the theory is equivalent to a different universe, which is actually much bigger than the Planck. In other words, even though the universe looks like it's shrinking if you shrink it down, in a effectively equivalent description takes over, which is actually expanding. So this is not a bounce solution, just to clarify. Some people in GR have talked about a situation where the universe undergoes a bounce. That's not what I'm talking about. The universe continues shrinking if you went back in time in the model I'm talking about, but that gets a bad description. And a better description is this other universe, which is actually opening up. Not in the same variables, but the dual variable. What that means is in the dual variables, what we call momentum states, particles having a momentum, in the other universe correspond to winding of strings around the other circle. And whereas the momentum of the other universe is what we would have called the string which is wound around one side of the universe to the other. So the degrees of freedom have completely reshuffled. So the statement is that if you went back in our universe in the early time, the momentum modes freeze out because they're so heavy, but the winding modes, which are not part of our universe locally because they're winding across the topology, which are local in this other universe, will emerge. So your description would look like Einstein's theory in a different universe, which is actually growing if you went back in time. And so the conversion from those modes to ours will be what you would have called reheating of our universe. Conversion of winding modes of our universe strings to the momentum mode strings by annihilation. So that's a picture. I don't know if that's the correct picture for our universe, but something like that may very well happen.
Thank you.
Are there more questions? Yeah.
So since there's a prediction that gravity acts as 1/r3, whereas the Coulomb, the electricity acts as 1/r2, would we expect to see anything in our nature where compositions are bound by gravity rather than the electricity that makes chemical stuff?
I'm not sure completely understood that. First of all, let me explain before I see if it's related to your question. You can explain whether it's the same as answering your question or not. When I said the gravity becomes 1/r cubed, if the electric forces were also propagating in the fifth dimension, it would have been also true for the electric potentials to become 1/r forces to become 1/r cubed as well. However, I was explaining that our universe has to live on a subspace of the fifth dimension. Therefore, it does not go like 1/r cubed. So the Coulomb force, even if you go down to the distances less than a micron, it's still 1/r squared, and we have plenty of evidence of it. Atomic physics. Atomic physics would not have worked if it was a different power law at 1/r squared. That we have checked it in Schrodinger's equation. So that would have been manifestly false. So I'm not saying that the Coulomb force would change. That's still 1/r squared at the micron scale.
And what I'm asking is that since it doesn't change, would we expect to see anything special in very small scales that would naturally occur?
Well, if the atoms, if somehow the gravity was strong enough to overtake, yes, but it doesn't, unfortunately. It's very weak in atomic scale, even if you put 1/r cubed.
So one question over there and then.
Thank you for the talk, Professor. I was actually wondering back to kind of the beginning part about the string theory itself. Do you know anything to do with, I suppose, the detection of strings, like the experimental verification of string theory?
What could be, you mean?
Yeah, like and methods towards.
Well, I
detecting
gave,
string.
I hope I gave a few examples of it. One, the simplest one, if it's possible, is this 1/r² force law, which would be one vindication. Another one would be the relation between dark energy, and if it evolves, whether or not the slope of the potential has anything to do with the value of the potential. That's another one which is beginning to already be observed. Other things could be the predictions of the magnetic monopoles math. Could we have detection methods for magnetic monopoles or creation? I don't know. So there are a bunch of things that you can potentially put together, and not one experiment will settle things, of course. But I think if you see a coherent story emerging, then that would be the verification of it.
We have time for one more question, but okay.
Thank you for your talk, Professor. I'm just wondering how many more years it is expected to finish the experiment with rotating oscillator with pendulum.
That one, as I said, for the 10 micron regime where they're aiming, they say 2 years from now. That's going to be up to 10 microns. I've asked them whether they can push it down to 1 micron, and they say it's very difficult. So they don't think that experiment can be pushed down to 1 micron. Now, I do not know the exact size of the extra dimension. It's 1 micron, it could be near 10 micron. So there's a chance they might see some effect already in a couple of years. But I would have loved if they could, that or some other experiment can push it to 1 micron. The 1 micron experiment, I don't know what the time scale for the 1 micron is, but 10 micron is going to be 2 years.
Okay. Once it's done, will it going to be the first experiment in terms of in the field of string theory? Because I've never heard of any experiment that relates to string theory. That's why I'm interested in it.
Sorry, what is the?
If that experiment with pendulum
Yes.
is done,
Yes.
is it gonna be the first experiment ever?
Well,
in this field?
I would say it's an evidence. You see, in physics, we don't prove anything. But by that I mean we find evidence for theories. So that would be one evidence in that direction. But everything could have alternative explanations. So somebody says, oh, even if you say that, then I can think about something else which explains nothing to do with string theory. So I think just physicists are cautious people. They don't say everything suddenly falls by one observation. But if you have a coherent set of things, then yes. Then if the dark energy behaves the way I'm saying, if that works the way I'm saying it, then you begin to say, oh, it sounds like a good picture. So that's how you build confidence. If it doesn't, then it doesn't.
Okay, so, yes, one last question. Sure. Behind you.
Was wondering, how come you can delineate between what's a good and bad QFT using on the basis of string theory if string theory hasn't been proven yet?
So string theory, good question. So when I say string theory has not been, when you say string theory has not been proven, depends on what you mean. I think we have a lot of evidence that examples within string theory are consistent vacua of quantum gravity. When you say proven, usually when what people say string theory has not been proven, what they mean that we haven't proven that our universe can be obtained from string theory. That's what they usually mean by string theory has not proven. It means experimentally proven. String theory has been proven to reasonable definition of proven theoretically. So theoretically, string theory makes sense. Namely, we have full confidence that theory exists. Whether that's the theory of our universe, it's not been proven. That's what's true. So there's no debate that string theory is a consistent theory of gravity. We haven't proven it in a mathematical sense, but I think in a physical sense, people believe it. That's not we have a huge amount of evidence for that.
Okay, thank you.
Okay, well, let's thank Herman again for a really nice talk. And I think we should thank both Welsh lecturers for
Thank you.
a really outstanding illuminating set of lectures this year.
Thank you.